SwayamPrabha. Digital India. Educated India.
If you remember, in the last week's lectures we were looking at stability. We ended with interesting examples, alright, of stability that is attractive but not stable, asymptotically stable, globally asymptotically stable, non-uniform stability, and so on and so forth. Okay. And then finally what we had done was we had sort of proved some simpler results for linear systems. Okay. So, what were these simpler results? It sort of characterized stability in the form of bounds on the state transition matrix. Okay. But in spite of all of this, we sort of explained, and I hope all of us understood that this sort of characterization is still a definition of stability. Okay. It should be considered a definition of stability and not necessarily a test of stability, because using these definitions is not very easy. Okay. For time varying linear systems, you will still require to solve the system in order to get state transition matrices in order for us to be able to talk about boundedness. Okay. So, these are still to be seen as definitions and not as tests, and that is where we are going to move on to this week. So, we start with our material on Lyapunov theorems. Okay, you can see that I am using my earlier NPTEL notes. So, these parts are, there is some commonality here. Of course, there is a we will look at a little bit more detail on some proofs, but that will come probably later this week, or actually it won't come this week, it probably come next week. Okay. So, like I said, I am out on Friday, so we will not have a class on that day. Alright. So, let us first look at the results, alright. We just look at the results, how to use them, and we will look at the proof of one or two of these results later. Okay, that is the idea. That way we are, we have some handle on what we are even trying to do. Okay. So, as I had mentioned very clearly, I think that there is a problem with stability definitions. We have to solve the system of equations. Okay. Now, this has to be the case, because if you are using epsilon delta of any form, you will have to solve. Yeah, whatever examples we took, we actually solved the system. Okay, and which is not possible for most nonlinear systems. Okay, and so we are looking at actually not quantitative, but I would say more qualitative methods. Yeah, but anyway, I'll leave this word as it is, because depends on how you think about it. Okay, all right. So, before we go on to talk about the Lyapunov theorems, we need some background. Okay. So, we first talk about function classes. All of you already know a few function classes, by the way. These are characterized by the LP norms, the capital LP norms. So, you already are aware of some certain function classes. Yeah, these are additional function classes that we are going to talk about. So, so I hope you keep in mind that there are several kinds of categories of functions that we tend to invoke in all our analysis. Okay. So, what are these function classes? The first one is a class K function. Okay, and all of these functions are defined from R plus to R plus. Okay, so non-negative reals to non-negative reals. Okay, R plus denotes non-negative reals, so 0 is included in this set. Okay, so a function phi is of class K if it is continuous, strictly increasing, and it is 0 at 0. Okay, that is it, only these three conditions. Okay, examples are like it's mentioned here, 1 minus e minus x and x. Why? You can verify when x is 0, this is 0, right. So, here also I have mentioned, if you take phi x equal to x, this is one of the simplest examples, right, because it is 0 at 0, it is definitely strictly increasing, right, you can take a partial and see, and it is definitely continuous, in fact it is smooth. Yeah. Similarly, you can take any other polynomial. You can imagine that any polynomial would work. Yeah, polynomials are in fact analytic functions, so way more than smooth. Yeah, they're even beyond smooth. So polynomials all work. Yeah, as long as the coefficients are positive and all the nice things happen, right? Otherwise, it might be decreasing. Yeah, that is a problem. So typically, if you take x square is also fine. Okay, it's also an increasing function. Yeah, because we are looking only at 0 and beyond. Yeah, arguments are non-negative reals. Okay, so therefore this works. Yeah, so this also works on the negative side, but if I take x cubed and all, then there is a problem. Alright, okay. Then finally we have a function which is of this kind, 1 minus e minus x. I keep using this example, even for supremum I use this example. It actually turns out to be a very nice, interesting function. 1 minus e minus x, if I take partial with respect to x, it is what? E minus x, which is positive, right? Whenever x is non-negative and as long as x is not infinity, and infinity is anyway not part of real, so we are fine. Okay. So therefore this is a also a continuous function, in fact smooth again, also a strictly increasing function, and it's 0 at 0. So all three functions satisfy these criteria. Okay. Is that clear? This is what is a class K function. Remember, arguments are always scalar valued, non-negative reals, and the output is also, or the image is also scalar valued, non-negative reals. Okay. So scalar valued functions are all we are talking about. Do not ever design a vector valued function or a vector argument function and think of it as class K. No. Okay. There is no such characterization. Alright. Class L function. Sort of a flipped version. A function phi, again you see that this never changes, is class L if it is continuous, strictly decreasing, and it is, the initial value is finite. Okay. An example is 1 over x plus 1, because at 0 this is of course 1, it is strictly decreasing is evident. Right, because as x keeps increasing, again remember x is in R plus, right, as x keeps increasing this keeps decreasing, obvious, and it is continuous, continuity, you can also verify continuity, yeah, because it is, there is only continuity issue at x equal to minus 1, but that is not a valid argument, so it is fine. Okay. One of the things that we need to note is that if a function is class K, then it does not mean that the negative is class L. Okay, I hope this is sort of obvious, because as soon as I take a negative, my image lies in R minus, yeah, which in itself is not allowed. Okay, so as a definition it is not allowed. Yeah, so negative of class K function is not a class L function. Alright, so negative valued functions we do not use. Yeah, this is just a, why we talk about these functions is these are what make up Lyapunov functions. Yeah. And Lyapunov functions, if anybody has ever seen, these are actually like energy like functions, and we never talk about negative energies, well, not in our community. I mean, maybe in quantum we can talk about it, but I am not an expert there, so I can't comment on it. But yeah, here we don't obviously have notions of negative energy. So Lyapunov functions typically have connotations of energy, so obviously we don't allow negative valued quantities here. Okay. So class K and class L, two characterizations. Now we have another characterization which is a sort of a stronger characterization. It is a class KR function. Okay. A function, again same arguments, is class KR if it is class K and it goes to infinity as the argument goes to infinity. Okay, that is it. This is the only additional requirement. Okay. So one of the examples we considered for class K deliberately was this, and that function looks like this, strictly increasing by the way, no problem, but it maxes out at 1, alright, never exceeds 1 for whatever value of the argument, right, because plot looks like this, keeps getting closer and closer to 1 but never actually hits 1, yeah. So this is not class KR, because even though the argument becomes infinite or tends to infinity, we are all talking about tending to infinity, your function value will tend to 1 in fact, yeah, so not infinity. So these are, there is a certain limitation about these functions, that is why they are only class k, yeah, and not class kr. But if you take these polynomial functions that we looked at, they have all the nice properties, right, it goes to infinity as the argument goes to infinity. So these are in fact class kr functions, okay. So as we move on, you will see that class k functions are connected with notions of local stability or stability. Class kr functions are connected to notions of global stability, okay, and class L functions are connected to uniformity, okay. So these are the three classes of functions, and then the three kind of stability definitions we have seen. Everything else is a sort of combination of all this, right, because you say that you have some kind of stability, uniform stability, global uniform stability, and then there is the qualifiers of asymptotic and so on and so forth. That is okay, that also we will see how they are connected, okay. But local stability typically class k tested via class k functions, global stability via class kr functions, and uniformity using class L functions, alright, okay. So one of the key things that anyway I've already mentioned is that we assume an equilibrium of 0, okay, we assume the equilibrium to be 0, alright. Say that again. No, R is just I've just, instead of using X, I've just used R, just the argument, okay, I've just changed the labeling on the argument, alright. So it's a class R function, sorry, it's a class kr function, not that R, okay. This is just some notation for the argument, yeah, I've just replaced X by this, yeah, alright, okay, great. Now we are in a position to talk about definiteness, okay. Once we have defined these class k functions, class kr functions, we can talk about definiteness, okay. Before I even go to definiteness, I hope all of you, we just looked at it a couple of classes ago, for matrices, symmetric matrices, you have very clean and clear notions of definiteness. Here you have this notation, by the way, whenever I use this notation, this means that the matrix is positive definite, right, because there is no idea of positivity of matrix otherwise, right. So whenever I use this notation a greater than 0, it means I am saying that the matrix is positive definite, okay. You also know that it means that the quadratic forms are always positive for non-zero x. You also know that the eigenvalues of A are always positive, and all principal minors have positive determinant. Yeah, we exactly looked at these three characterizations, okay, for positive definiteness of matrices. Now what we want to do is generalize positive definiteness of matrices to functions, okay, because again those of you who had exposure to doing internal stability for linear systems, you know that you use something like the Lyapunov equation, right, and the Lyapunov equation essentially looks like what? It says that, right, where Q is and Q and P are symmetric matrices. So given, so the statement of course goes more formally like, given a Q there exists a P which solves this Lyapunov equation. Yeah, why this characterizes stability is because you choose your V, a Lyapunov candidate, in fact a Lyapunov function in fact, as X transpose Px for the system, right, and if you take a derivative of this V dot and your system is governed by x dot equal to Ax, because this is the system for which you are studying the stability, then V dot is actually turns out to be X transpose Pa plus A transpose Px, okay, alright, okay, makes sense. And this, yeah, is in fact I did not write it completely, this is positive definite, this is positive definite, okay. You actually require that given any positive definite symmetric Q, you can obtain a positive definite symmetric P which satisfies this Lyapunov equation, okay. And once we have that, essentially what we are saying is that this becomes a positive definite function, right. It is a sort of extension of positive definiteness from matrices to functions. So this is now a function of x, right. So this is what we want to connect. Now we want to say that we may have more general forms, okay, than x transpose px, something quadratic, something simple, because nonlinear systems have a lot of different structure, right. You can't necessarily say that for every nonlinear system I can use a quadratic Lyapunov function, alright. That's in itself a big assumption. If you say that there exists a quadratic Lyapunov function for a nonlinear system, that's a very big assumption already, yeah, because you are somehow saying that you can use linear notions to analyze this nonlinear system, okay. So anyway, so the point is we want to have a more general characterization of positive definiteness for functions, okay. Okay, great. So that's where we are going, that's the aim here. So definiteness, what does it mean? It says that positive definiteness requires that you have a scalar valued continuous function which is of time and of some states belonging to a ball of radius r, that's this guy, right. This is what is the ball of radius r, we have already spoken about it. If you use different norms, you will get different shapes here. You can get, in general you can think of it as an ellipse, yeah, or a circle, but you can also get square and rhombus and whatnot depending on the norm you choose, okay. But it is a ball, we keep calling it a ball of radius r, okay, yeah. Otherwise we have to say neighborhood and all that, yeah. So that makes life a little bit more complicated, alright, great. So we want this function v, and this is the most standard notation you will ever find, of time and states belonging to a local region, and it maps to real numbers, okay. It is always scalar valued. So energy, like, yeah, again energy is the most, if you think kinetic energy, potential energy, scalar value, take in the states, give you some scalar value, okay. So that is the most obvious characterization of V, yeah. But remember, in more often than not we do not use the energy of the system as V, okay. In several cases we do, but many more times we do not, alright, okay. What do you require from this? This is, as of now I have only defined the domain and the range, okay. What do I require? I require that it is 0 for 0 states, okay. The function has to be 0 valued when the states are at 0. It is almost like a norm condition, remember, yeah, has to be 0 when states are 0 for all t in R plus, okay. It does not matter what t is. If I put 0 states, it is almost like saying that at equilibrium, if my right hand side of the system is 0, then this function which I am trying to use to analyze the system cannot be non-zero when the states are 0, okay, does not make sense. So it has to be 0 when the states are 0. There has to exist a class k function phi such that this function dominates phi norm of x. Notice how the class k function has been used, okay. I mentioned very clearly that the class k functions have domain and range as non-negative reals, okay. So, but we are talking about states, so how do we compare? We use the norm of the state as the argument, okay. The argument of a class k function will always be the norm of the state. It can be a weighted norm, no problem, yeah, but it has to be a norm, okay, alright. So why? Because the norm is always non-negative. So by virtue of taking the norm, I made the argument non-negative, okay, alright, great. So important thing to remember is that this does not mean that V is strictly increasing. V only has to dominate a strictly increasing function. Notice this, look at this picture here. V does not have to be strictly increasing itself. If I think of phi x as this function, a strictly increasing continuous function which is 0 at 0, and V itself is also 0 at 0, V does not have to be strictly increasing. It can oscillate, but it has to remain above this line. Also remember, my states were always required to be in this ball, bounded ball. Therefore, this domination also does not need to last forever. It only needs to last until the norm of the states, in fact this is not x but this is norm of x. Yeah, this only has to last until the norm is less than r. Beyond that it does not need to last. Okay. So, two things, this characterization number 2 does not mean that V is strictly increasing, only requires to be bounded by a strictly increasing function and does not have to be bounded for all states. Yeah, it has to be bounded only for certain states in a certain ball of radius r. Okay, that is how we are doing this characterization, and that is it. This is what is positive definite function. This is how we define it. Okay, we have still not connected it with the matrix definition for linear systems. We'll go there. Okay. So of course, like I said, positive definiteness will connect to asymptotic stability. We'll look at how. Don't worry about it. Now, if you look at if you think of this norm x, and then you know norm x is something like this. This is the 2 norm, for example. Okay. Then a phi norm x is basically if you can think of phi norm x as something like this. This is a class k function, remember. I hope you are convinced this is a class k function. Yeah, I am sort of using this, I mean going reverse and constructing a V, a positive definite V, by the way. Usually that is not the case. First you are given a V, then you have to think of a phi. I am sort of going the opposite side just to give an example. Okay. You know the 2 norm, just the Euclidean distance, and then suppose I construct this class k function. This is a class k function. I hope you are convinced. Is anybody not convinced that this is a class k function? All you have to verify is that it's 0 at 0. It is strictly increasing. Do you believe it's strictly increasing? Yeah. This can be written as 1 minus 1 over norm x square plus 1. It's strictly increasing, and it has to be continuous, or it is continuous in the norm. Yeah, not difficult to see that it's continuous in the norm. Yeah, only issue would have happened here, but there is a square here, so obviously not an issue. Okay, so this is continuous, strictly increasing, 0 at 0, valid class k function. So if my Vtx is something like this guy, yeah, then this is going to dominate phi norm x, yeah, for all t greater than t in r plus. Okay, for all t in r plus, this is going to dominate this guy. So this V is a positive definite function. Okay, notice how different it is from your linear system sort of positive definite function. Characterization is rather different. Okay, I hope that's clear.